In this video, we're going to find zeros, turning points, and increasing, decreasing regions of a function. So today we're going to take a slightly different approach to identifying the x-intercepts of a polynomial function. And we're going to use something called the location principle. And the location principle states that if f is a polynomial function and a and b are two real numbers, so two x values, such that f of a, or the y value for a, is less than 0, and the y value for b, or f of b, is greater than 0, then f has at least one real 0 between a and b. Now, I have an example here because to me that's kind of a confusing sentence and doesn't necessarily make a ton of sense. But what I'm looking for is I'm looking in a table of values, and I'm going to look at my x values. My x values are always going up by 1, so I can see that I'm moving on my graph from left to right. And what I'm going to look for on my y values over here is I'm going to look for a change from positive to negative or negative to positive. And if there's a change of signs of my y values, I know that there is a 0 in between. And then I can start testing some values in between. So here what I notice is that between -1 and 0, it switches from negative to positive. And because of that, I know that there is a 0, a real 0, in between here. Now, I don't know what that real 0 is at this point, but because I have a leading coefficient of 12, I know that this number can have a denominator of 2, 3, 4, 6, or 12. It can also have a denominator of 1, but that would make it an integer. So I know that there's something between -1 and 0 that is resulting in a x-intercept. I can see that from the change of positive to negative. Now if I look at the next set of y values, I notice that again I go from positive to negative. So that tells me that there is another 0 here between 0 and -1. So I found one between -1 and 0. I'm then finding one between 0 and 1. And again, it's going to have these denominators here. Then if I keep looking, I notice, okay, this is negative, this is negative. So because there's no change, I have no guarantee that there's a 0 between those. But then here, because this is a change from negative to positive, I can again see that I have another 0 between 3 and 4. So the location principle just tells us that we can utilize a table and the y values to help narrow down exactly where our x-intercepts or our zeros are going to be. In this video, we're also going to take a look at turning points. And turning points of a polynomial are defined as the points when the polynomial changes between increasing and decreasing regions. Now remember, increasing or decreasing regions, we read a graph from left to right. So we're looking at, as we read the graph from left to right, where does it change either from increasing to decreasing or decreasing to increasing. And those are called our turning points. And if I look at this particular graph, I can estimate 2 of them. I can see one turning point right here and one turning point right here because the graph here was increasing. I can see that it was increasing, 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 and then it changed to be decreasing, 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 and then it changed back to being increasing, 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 increasing. So because there was that change from increasing to decreasing or decreasing to increasing, I can see that I have a turning point. Now there are 2 types of turning points that we can have. One is called a local maximum, and that occurs when the point is higher than all of its other nearby points. So it's not saying it's the highest point on the graph, it's just saying that locally around this point, it is, compared to the points that are nearby, the highest point. And when I look, I notice here that this point right here is a local maximum because all of the other points around it are below it. It is the highest point in its region. So locally, amongst the points around it, it is a maximum point. Then on the flip side, we also have a local minimum, which is when the point is lower than all of its other nearby points. And if I look at the graph here, what I notice is that I have a local minimum down here. While this isn't the lowest point on the graph, it is locally a minimum. It is locally lower than all of the other points around it. So turning points will either be a local minimum or a local maximum. One more thing to note about turning points is that the graph of every polynomial with degree n, so whatever its degree is, it has at most n minus 1 turning point. So for example, if we have an x to the third is our degree, it's our highest degree, then we're going to have 2 or less turning points. And it all ends up depending on, bounces that you have and complex solutions and everything like that. But you're going to see if we have an x to the third, you're going to have 2 or less turning points on your graph. So we're going to utilize the location principle here to start estimating what some zeros might be. So here we can see that we have a polynomial function that doesn't have nice coefficients. Those coefficients have decimals, and so we're going to need to use a calculator and the table and our graph to start to estimate where these x-intercepts might be. So here if I look, what I'm looking for is a change in f of x where it goes from negative to positive. So what I notice as I go through my table over here and I pay attention to these y values, I notice that there's got to be a 0 between negative 3 and negative 2 because there's a change from negative to positive. I also notice there needs to be a 0 between negative 2 and negative 1 because there's a change from positive to negative. And then I notice there probably needs to be a 0 between 1 and 2 because there's a change from negative to positive. So what we can do is we can highlight these three regions, we can utilize our graph, and we can start to estimate what these might be. Now you might have to try a couple of points utilizing your synthetic division, but you can use the location principle here to help you estimate what these zeros might be. So in this case, if I were to start, I would probably start with halves and then break down into other variations of fractions and things I could test. So here I'm going to start by testing off negative 5 over 2 because that's going to be a negative 2.5 and that's between those. I'm also going to test out negative 3 over 2 because that is a value that's negative 1.5 and that would be smack in the middle of those. And then here I'm going to try a positive 3.2 because I know that that is the halfway point between 1 and 2. So again, I'm just picking values that are between, and if those don't work, I'll pick new ones based on what I'm seeing on the graph. So here if we utilize synthetic division, we can double check and see if ours are correct. So I'm going to start with negative 5 over 2. I'm going to put down my coefficients here. And then from here we can start going. So I have 1, I bring it down, I multiply that by negative 5 over 2. Remember, if you need to, this is really a negative 2.5 if we divide that out. Multiply that by negative 2.5. And we're going to add straight down, so that's 0. Then multiply that by negative 2.5, which is 0. Add straight down, which is negative 2.25. Multiply that by the negative 2.5, and you end up with negative 5.625. So we can see that our guess was correct, and we have a 0 at negative 5 over 2. Now, if that didn't work, you could go ahead and you could try a different value between negative 3 and negative 2, maybe using the graph to estimate is it a little bit more to the right or a little bit more to the left. So what you're going to do with the location principle is just use that to help you estimate what your zeros might be. So you can utilize the graph, you can look at the table. What you're looking for is a change between when y is negative and y is positive to find all of the zeros. Now, I'm not going to officially go through this one in full. You would go through this same process for all of your guesses. And if you found that a guess didn't work, so say 3 over 2 doesn't work, say if that happens, then you continue to guess a different y value between there, maybe changing the denominator, creating a new guess. So your goal is just to use a little bit of guess and check tied with synthetic division and some very purposeful guessing based on the location principle to help you find your zeros. So these are going to be not so nice zeros that are fractions that you can use the location principle plus graphing, plus the table, plus synthetic division to help you find. So what we're going to do here on this last slide is we're going to estimate our turning points of our graph and then describe the increasing and decreasing regions. So in class, I'm going to show you how you can utilize a calculator to accurately 100% find what that turning point value is. Here, we're just going to kind of estimate. So here I can see that my first turning point here occurs just a little bit smaller than x is negative 2. So I'm going to guess that my turning point number 1 is going to be at about, we'll say, negative 2.1 comma 0.9. I'm guessing here. This is just an educated guess. As I said, we're going to look tomorrow at how we can utilize a calculator to accurately find that value, but that's my guess right now of what that turning point is. Now, because this turning point is the highest point in its particular region, this particular turning point is a local maximum because it is locally higher than all of the points around it. Now, if I look at my second point here, I'm going to estimate what this one is as well. It looks like it is a little bit less than half. So it looks like my x value might be about 0.4. And then my y value is a little bit lower than negative 6, so maybe about negative 6.1. So that's what I'm going to say there. So turning point number 2, I'm estimating, is about 0.4 through negative 6.1, and that one is a local min because of its location. It is locally lower than all of the points around it. So those are our turning points. We're just estimating them for now. Later we will learn how to utilize our graph on our graphing calculator to accurately find what they are. Now, the last thing we need to find are the increasing and decreasing regions. And remember, we read graphs from left to right, and our increasing regions occur whenever the graph is going up. So here I can see that starting here, and it's kind of going down to infinity, all the way up to this x value of negative 2.1, my graph is increasing. So I have an increasing region here. The graph is increasing all the way from negative infinity up to 2.1. So all of those x values are the x values that are lower than negative 2.1. It's also increasing over here as we start when the x values are at 0.4 and get bigger. So I can see I have two increasing regions, one when x is less than negative 2.1 and one when x is more than 2.1. Now, my final thing here is I need to find my decreasing regions. And if I look, I notice that the only spot where I am decreasing is right here, sandwiched between my two x values of my turning points. So here my decreasing region is going to be represented by a compound inequality. And that's where x is on the smaller side of 0.4 and the bigger side of negative 2.1. So basically my decreasing region starts at negative 2.1 and goes all the way through until x is 0.4. So we can use our estimates of our turning points to find where our graph is approximately increasing and decreasing.